Radical substitution is one of the first reaction mechanisms that we're going to look at in AS chemistry, and it's also quite a tough one. A reaction mechanism is something which shows us the path of electrons as we go through a particular reaction, and there are many that you're going to have to learn at A level. So let's jump into radical substitution. First, we need to know what a radical actually is and why it forms in the first place. Let's take bromine as our example, and I'm going to be using bromine all the way through the video. There are a couple of different ways that we can take bromine from Br2, its normal molecule, and change it into something else chemically. So one of the ways that you'll be familiar with from GCSE is that we can make it into an ion. We can cause it to gain an electron, and we can do that by adding something, I don't know, like potassium. Potassium is quite fun to add to bromine. It creates all sorts of fireworks, and the potassium ends up as a positive ion, and the bromine ends up as a negative ion, gaining an electron into its outer shell. The other way that we can do it is by actually just splitting this molecule apart. Now this is stable, ions are stable. What we form when we just rip the molecule apart is actually very unstable, and it's called a radical. And if you look at the diagram here, you'll notice that you've always been taught at GCSE that this shell has 8 electrons as its maximum, and things in group 7 have 7 electrons, and so it's a bit surprising that we actually have a gap here in the outer shell, but that's what a radical is. It's a species with an unpaired electron, and here is our unpaired electron. So the negative ion is a usual thing that you've seen before. It takes part in displacement reactions, etc. But this radical is probably something new, and we represent a radical by showing the unpaired electron on the atom that it's on. So here we have the unpaired electron on the bromine atom, so I'm going to put it on the bromine atom. It doesn't matter actually where around the bromine atom is, as long as it's on the bromine atom. So how do we create these things? Well, because it's unstable, what we need to do is we need to put in an awful lot of energy, and actually it's ultraviolet light that we need, ultraviolet radiation. If we give a sample of bromine enough energy through ultraviolet light, then we will split some of these molecules apart to just be naked atoms, if you like. They are missing an electron in their outer shell like this, and so they are incredibly reactive. They don't hang around for long because they tend to react with the first thing they come across. A couple of key words for you then. This is an example of a homolytic fission. Now, homo literally means the same. Okay, so we have 2 bromines here. A homolytic fission, fission meaning to split, would be if we took our bromine and 1 electron from this covalent bond went to this atom. I'm going to represent that with a 1-headed arrow like that from the bond, and then the other one went the other way. Again, a 1-headed arrow to represent 1 electron coming from the bond, and there we would end up with 2 radicals, and that's called homolytic fission. The opposite of that, just for completion, is heterolytic fission, hetero meaning different, and you'll come across that in other reaction mechanisms. This is where we have something which doesn't break evenly, so at the end we don't get 2 identical chemical species. What we get is we have both of the electrons in a covalent bond going in one direction towards one of the atoms, usually the most electronegative, which pulls the electrons towards it, and we will end up with 2 ions. Our radical mechanism then is going to show how the electrons are transferred throughout this chemical reaction, and we're going to start with a step called initiation. Now, whenever you are asked to draw a mechanism for a free radical substitution, make sure that you put the steps at the side of the paper so the examiner knows that you know the 3 different steps. The first step is initiation, where we use ultraviolet light, as we just said, to make 2 radicals of bromine. The second step is called propagation, and what we're doing is we're basically starting a kind of chain reaction. The bromine radical is going to come across some kind of alkane or whatever else we put in there, but for your course it's an alkane. We're going to take the bromine, we're going to react it with the CH4. Your CH4 is going to lose one of its hydrogens. We're going to end up with one of the hydrogens literally being ripped off. And that's going to leave the CH4 as a CH3 radical. One of its hydrogens has been ripped off to satisfy this insatiable need for this extra electron that this bromine has. It's going to basically poach the hydrogen from the methane molecule, leaving it kind of like, well, it's got an unpaired electron there. It's now unstable itself. But the bromine is now happily in a covalent molecule of HBr. And the second step of this is that this radical here that's now formed is going to go in search of something else in order to satisfy its unpaired electron there. It's now a reactive radical. Whatever it collides with, it's going to react with. And so we put that as a reactant on the next line. This is our product that's going to whiff off into the reaction mixture. The next thing that this is going to encounter, which it will react with, is a second Br2 molecule. And the Br2 molecule is going to be attacked by this radical. We're going to now rip a bromine out of this molecule, leaving us with CH3Br, and the second bromine in the molecule is going to be left with an unpaired electron again. And the last step is called termination. Termination is where we take finally our radical and we react it with something else so that it stops being a radical. Well, what will that be? It could be a number of things. It could come across another Br radical, and if those two come together, it will react to form Br2 again. And we might find that that goes back into the reaction mixture, and we can use that to make more of our product. The other thing that could happen, of course, we haven't just got bromine radicals there. We actually have a CH3 radical as well. So if the random collisions end up with a bromine radical and a CH3 radical coming together, they will also terminate each other. They'll share this pair of electrons in a covalent bond, and we'll end up with our product again, which is good. Slightly less desirable than these two is the third option, which is that actually two CH3 radicals could come together. Now this is undesirable because what we want to make in this reaction, we're trying to substitute a bromine onto a methane molecule. What we don't want to happen really is two methyl radicals coming together, because in that case we would then make C2H6, which is ethane. Now that's going to be an impurity in our product, and so that's less desirable. However, it gets worse. In the propagation step, there's no reason that the first molecule the bromine radical comes across has to be the methane that we want it to react with. It could actually react with something else. Now, it could react with this to terminate, and we've seen that before, but it could also react with the product. If the product happens to be the next molecule, we end up with the bromine radical reacting, instead of with the methane, we react with the product, and that will produce a second type of organic radical, which is now going to have a different hydrogen ripped off it. So we're going to have a radical with an unpaired electron on the carbon atom. We're going to have now two hydrogens on there. We're going to still have the bromine that we had before, but the other hydrogen has been ripped off, and we're going to end up with HBr. And then this radical will do the same as the original methyl radical did. it will try and find a way to share that electron in a pair, and it will come across probably something like another bromine molecule. And that means that we'll actually end up with CH2Br2 and another bromine radical. So the radical is still being recycled here. We're still getting it out of the reaction as much as we're putting it in. And the problem is now we've actually got two bromines substituted. In fact, if I start with methane and I add some Br2, I can make some CH3Br. If I add more Br2 to my reaction mixture, I can actually substitute twice. If I add even more, I can substitute 3 times, and if I add even more, I can substitute 4 times, and we can end up with tetrabromomethane. But that's just methane with 1 carbon atom. If we have 2 carbon atoms, even just 1 more carbon atom, we end up with all of these possible products from radical substitution. We could have a single substitution, or a double, or a triple, or a quadruple, or 5 or 6 substitutions, and so we get a huge mixture of products. And for that reason, this really isn't a very useful synthesis, but it is one of the only ways to get an alkane to react. In your propagation stage, your products are the HBr that's produced in the first equation, the organic compound which is produced in the second equation, and if there's more substitutions, and we could carry on with 3 or 4 down here, we go for another HBr there and the organic product there. So however far you're going down, you have your organic product and however many HBRs you've made along the way. So in this case we would have 2 HBr made and this organic product. So to work out your overall equation, you need to say, right, okay, well, what was the original chemical we put in? We put in methane. And we put in bromine. What did we get out? Well, with 1 substitution, we got our organic product, CH3, with 1 of the bromines substituted a hydrogen, so we got CH3Br. What was the second thing produced in the reaction? Well, the Br radical went on to go back into another reaction somewhere, so we're not going to count that as a product. The organic chemical we have here, the only other thing that we've got is the HBr we made in the first step. That is our overall equation for a single substitution. If we had 2 substitutions, then we started with methane, same as before, and this time if we look down the propagation equations, we have put in 2 Br2s into the equation. We've got out our final di-substituted organic product, and we've released 2 HBRs. And the pattern continues. If I put methane in and I had 3 substitutions, I'd have 3 Br2s, have a tri-substituted methane, and have 3 HBRs at the end, and we could take that all the way to 4 substitutions.